Hello, everybody. My name is Nazarbayev. I am from Physics Department and Energetic Cosmos Laboratory of Nazarbayev University. I would like to welcome everybody to the first colloquium of the Autumn Colloquia Series of the Energetic Cosmos Laboratory. We'll have a nice 1-hour presentation, and I would like just to mention that if you have any questions during the presentations, please feel free to write your question using this Q&A button. This lecture will be recorded and made available later. Okay, and with that, I will give the floor to Loretta Ondodel, Vice Provost, who will introduce the speaker. Thank you.
Thank you very much, Anasa, and welcome, a very, very warm welcome to all our audience members tonight. Whether you're in the Sultan, whether you're around Kazakhstan, or wherever you are in the world, you are very welcome to this public lecture. As you may know, this lecture is held under the auspices of ECL, which is the Energetic Cosmos Laboratory, which is part of the Office of the Provost here at Nazarbayev University in Nur Sultan, the capital city of Kazakhstan. And we're very fortunate that ECL has a range of very prestigious scientists, including Eric Linder, who's here tonight, and many other great people, including George Smoot, former Nobel laureate in physics. And it gives me great pleasure to welcome our keynote speaker tonight, Dr. Katie Mack, who happens to be physically in Massachusetts at the moment, but would normally be in North Carolina, if I'm not mistaken. But she's in Massachusetts tonight at a fairly ungodly hour of the day because she is passionate about her work as an astrophysicist. I'm going to give you just a little bit of a background about Katie, and then she'll be talking. And as you heard from Ernazan, there will be a Q&A session afterwards. And I would just reinforce the message he made. Don't use the chat button, but use the Q&A button. That's actually much easier when we have such a big audience as we do tonight. So please use the Q&A button for your questions. But let me talk to you just a little bit about the wonderful Katie Mack, and I think you'll agree how lucky we are to have her tonight. Just simply, I'll talk about her CV, but it doesn't begin to explain the sort of person that she is. But simply, Katie completed her undergraduate degree in physics at Caltech, and then moved on to do a PhD in astrophysics at Princeton, where she graduated in the year 2009. And her thesis was supervised by Paul Steinhardt, a name I'm sure many of you are very familiar with. She then moved on to Cambridge University for her postdoc and worked in the Kavli Institute for Cosmology. She had some time in Australia, which is my home country, as a discovery early career researcher. And that's the DECRA Award, which is very prestigious and very competitive. So she was based at the University of Melbourne and spent a lot of time working with some of the Australian physicists down there. In 2018, she became an assistant professor in physics at North Carolina State University. But what's really interesting, I think, and says a lot about Katie's character as well as her scholarship, is that she's very much involved in the leadership and public science cluster at North Carolina State University. Now, some of you might know Katie from her outreach on Twitter and other social media platforms, but I would very strongly encourage you to have a look at a recent book that Katie has published. It's got the great title, The End of Everything, Astrophysically Speaking. A great, great title for a book. It was published just in August of this year, and it's available through the Apple Store, so it's easy to get from Kazakhstan or anywhere else in the world. But I think that Katie's great gift is that she's well known as a popular science communicator. And I think that speaks to a very deep level of scholarship. Someone knows their field so well that they can make it simple, not overly simple, but just the right level of simplicity so that anyone coming to the discipline of cosmology, understanding black holes, and in her case, understanding the end of the universe, can grasp it and understand it and play with it. So Katie is very playful with her ideas. She makes complex theories and complex theoreticians seem very accessible and very easy. And I think just a little bit more about Katie, apart from her scholarship, because she's a very very accomplished person. She was, some of you may be interested to know, in the opening credits of the movie Legally Blonde, which was filmed at Caltech, not at Harvard. So that busts one theory that some people might have had. Her mother was a great fan of science fiction and obviously really encouraged her in the profession that she's chosen. And I was interested to see, Katie, that you dedicated your book to your mother. And I think that speaks so well of a parent's role in encouraging the love of science. And I also discovered that your father worked on the Apollo 11 mission. So clearly... My
grandfather.
Oh, your grandfather.
Yeah,
that makes a lot more sense, actually.
Yeah.
So your grandfather worked on the Apollo 11 mission. So there's something in your DNA that says you think big, you think long, you think hard, but you certainly think big about the world. And what I loved about looking at your book in preparation for tonight's introduction is that you not only love physics, and you talk about physics with great passion and great interest, and as I said, great simplicity, but you quite cleverly and creatively bring in poetry, and you bring in literature, and you bring in music, and you bring in other elements of culture to help define and explain what it is you're thinking about when you're thinking about the end of the universe. You look at religion, and you look at the way religions consider the end of the universe and the end of time. And your book is a fascinating read. So as I said before, I'd strongly encourage people to look at it. It's easy to read. I'm not a scientist, I come from a business school, but I learned a great deal by going through Katie's book. And it just reminds me of a quote from one of my favorite physicists. And some people I know in the audience have heard me quote this before, but to me, it's really important and it's very relevant to Katie's work. So quantum physicist David Bohm wrote in 1965 that the purpose of science is not the accumulation of knowledge, but it is the creation of mental maps. And what Katie does for us is help us reimagine the mental map of the universe, not only its beginning, but potentially its end. And what an extraordinary way to think about the world, the phenomenon that surrounds us every day. I think it's very humbling. It's not sad, it's just beautiful. It's a humbling and very positive experience to read her work. So Katie, thank you so much for coming and being with us in our public lecture tonight. I just wanted to mention to you that we have this saying at Nazarbayev University, so I hope you can keep this in mind, that there are no stupid questions. So when you get to the Q&A session at the end, there'll be questions from all kinds of people, students, faculty, staff, the general public, but I'm sure you will appreciate that here there are no stupid questions, because everyone like you is searching for the big answers, the big picture. Where do we come from? Where are we going? So Katie, thanks again, and over to you.
Well, thanks so much, Layla. Thank you for that very, very flattering introduction, and I'm really glad to hear that that my book is so well received. Thanks again for being here, everyone. And I'm going to be talking about black holes. So this is this talk is, well, let me get the slides shared first of all, so that you can see what I'm talking about. Hold on a moment. Okay, hopefully you're seeing my title slide now. So this talk is about black holes and about some really exciting recent developments in how we understand black holes through really seeing them in new ways. And this image might be a familiar one to you, because this was the image from the Event Horizon Telescope. And it got a lot of attention when it was first produced, because it was our first real look at a particular aspect of black holes. And I'll talk more about that in a moment. But I want to just say in this talk a little bit about, where black holes come from, what we know about them, how they affect the space around them, what role they play in the universe. So this is kind of an introduction to all things black hole and really how we're starting to be able to see them in new ways. So okay, so let's start with how we make a black hole, right? So black holes are the result of the destruction of stars. So we have a star that is very near and dear to us, our sun. At some point in the future, our sun will sort of continue to evolve in its life as a star, and as it evolves in its life through its life as a star, it will expand and become much larger and redder and brighter. And as that happens over the course of several billion years, our sun will engulf the planet Mercury. It will engulf Venus, most likely, and it may destroy the Earth at that time. Before that, the sun will burn off the oceans of the Earth. Somewhere around 1 billion years, the Earth will become totally arid, and the sun will continue to expand. And over that time, it will eventually get so big and puffy that it'll blow off its outer layers. It will make what's called a planetary nebula, and the central part of the sun will collapse into a white dwarf. This is the kind of evolution that a star like our sun goes through. We've seen this process throughout the galaxy with other stars like our sun, making these amazing, beautiful planetary nebulae, and we've seen these white dwarf stars at the center of them. That is not going to make a black hole. So our sun, when it dies, it will never truly explode. It will throw off the outer layers, but it will never truly explode. It will not make a black hole. It will leave something else, a different kind of stellar remnant, this white dwarf star, this very compact little star, but it won't make a black hole. So in order to make a black hole, you really need something bigger. You need a larger kind of star. This is an illustration of sort of the range of sizes of stars out there in the universe. So this little red star is an example of something that would be about 1/10 the mass of the sun, 0.1 solar masses, a red dwarf star. Then we have something like our sun, and then there are examples of stars that are maybe 10 times as massive as our sun. There are even stars out there that are hundreds of times as massive as our sun, and so there's a big range in the sizes and masses of stars. And those different kinds of stars go through different stellar evolutions. So let's say we had a star that was maybe something like 20 times as massive as our sun. That star would blow up at the end of its life. It would create something that looks like this. This is called the Crab Nebula. This is the remnant of a star that has exploded, has sent out its material into this nebula, and this is not a black hole. When this star exploded, it created this big sort of cloud of material, and the central part of the star after that explosion became what's known as what's called a neutron star. So a neutron star is a kind of extremely dense star. It's one that in many cases is rapidly spinning and throwing radiation out its poles. And in this case, actually, we have an amazing view of the center of this nebula, in which there is this star, this neutron star in the center, and we can actually make movies of how it's throwing material out from the poles. There are these jets of material coming out of the poles. There's a disk of material around it where it's sending sort of shockwaves through the material around it. It's an amazing system. And it's the densest kind of object that can exist without being a black hole. So this neutron star is this incredibly dense, spinning extreme object, but it's sort of the last stop before becoming a black hole. So neutron stars, stars of the kind of mass, less than about 25 solar masses are things that will explode, will create neutron stars, but will not make black holes. In order to make black holes, you need something a little bit more massive. This is an image of a star that's about 30 times as massive as the sun, so 30 solar masses. And this star, we're pretty sure, is fated to give us that black hole eventually. So when you have a massive enough star, as that star reaches the end of its life, it collapses on itself, creates a supernova, makes a beautiful supernova remnant like this one, where it throws the material out. That material is lit up by the energetic radiation in that nebula, and then the central region at the point of that explosion can be so massive that there's so much material in such a small space that it collapses, and it has so much gravity that nothing can stop its collapse to a black hole. So what is a black hole? What are we really talking about here? Well, a black hole is a result of the way that gravity and space affect each other. So when you have a massive object in the universe, according to Einstein's theory, general relativity, that massive object bends the space around it. This illustration is a kind of typical illustration of the bending of space in the presence of massive objects. It's not a perfect illustration because this represents, space as a plane and a massive object as altering the shape of this two-dimensional space. We really have to imagine a three-dimensional space. So if I am a massive object, I'm distorting the space around me by kind of pulling it toward myself. So you can imagine all the space around me is kind of pulled in around me in a similar way to, as in this two-dimensional analogy, the space is bent toward that object. This is really Einstein's relativity. This is Einstein's theory of how mass affects space. And the thing about this whole model is that if the mass of an object is bending the space around it, then anything that's moving through that space has to move through that bent space in a bent path. Okay, so let's say that you have an object that's moving past a massive object in the universe. That object will follow a bent path because it will be trying to move in a straight line, but the space is not straight, so it will be bent around in the shape to follow the shape of the space. So, for example, we have this thing here, maybe a moon or an asteroid or something. It's moving toward this massive object, and the path it follows will be bent by the fact that it's moving through a bent space. And it turns out it's not just objects that have to follow the shape of space. Even light has to follow the shape of space. So if we were to shine a light past a massive object, it would also curve around as it's passing that massive object. This is a phenomenon called gravitational lensing. And basically anytime light is passing through curved space, that light itself gets curved around, gets bent around. And this can be very dramatic. I'm going to show a simulation, a visualization of what it would be like if a massive object passed between you and a background field of stars. So this is a visualization by Greg Egan, who is a science fiction writer and also a sort of mathematical physicist on the side. And this is a wonderful illustration he did of a massive object moving between you and just the background field of stars. You can see as that object moves through that it's distorting the image of the stars behind it. And so the stars themselves are not moving, but the space in between is being bent and curved. And so the light as it's coming through gets bent and curved around. And you can see that those sort of arcs and rings as that spherical massive object. This is just a simulation, but in principle, something like a black hole could make that kind of distortion of space. And And this phenomenon, gravitational lensing, is very, very common through the universe. We see gravitational lensing all over the place when any kind of massive object, usually a galaxy or a cluster of galaxies, bends the space that it's in. And so we see distorted images of the things behind it. And there's, it's a big universe. There's always going to be more distant galaxies that you can see that are being distorted by the galaxies and clusters of galaxies in the way. So, for example, this is a wonderful image of a cluster of galaxies distorting the light from galaxies behind it. And you can see that those arcs, as the light is bending around this massive region. And I want to show you specifically this blue little curved thing here. This is a blue galaxy that in actuality is right behind, directly behind this cluster of galaxies. But because the light is being bent around, because the space is so curved there, we see that little blue galaxy up here, and we see its light stretched all around here as it's moving past that curved space. And this here is also another image of that blue galaxy. So we see it in several places because of the way that the light is distorted, going around that cluster of galaxies. And then you see these sort of arcs over here and over here. These are all distorted images of background objects. So that's one of the ways that we can really see the presence of gravitational, gravitating objects in space. We can see how they distort the space around them. Now, the kind of distortion that I'm talking about for this kind of gravitational lensing, it's kind of a small bending of the space, really. A black hole is something that is so dense, or so compact and so massive that the distortion is really much more extreme. Okay, so the distortion of space around the black hole is so extreme that at some point that curvature is so steep that a really interesting phenomenon occurs. You end up with something called an event horizon. Now, an event horizon is where the curvature of space is so steep that it would take so much it would take so much energy, so much speed to escape from that region that it's impossible to do. The speed that it would take to escape from anywhere closer than the event horizon, the speed is more than the speed of light. So nothing can actually leave the black hole once it's gone past the event horizon. Now, just to illustrate this a little more, let's say you're looking at a black hole. There's a singularity in the center. So this is, well, theoretically, a place of sort of infinite density. So the idea is that once something falls into a black hole, there's no surface for it to land on. There's no object for it to run into. It just keeps getting compressed and compressed into the center, the central region of this black hole. So that's what we think happens at the center of a black hole. Now, we don't really know, and I'll explain why we don't really know what happens at the center of a black hole, but we think there's a singularity at the center. And then there's a distance from the singularity outward called the Schwarzschild radius, where the event horizon is. And the event horizon is that region where if you get closer than the event horizon to the singularity, if your distance from the singularity gets to be less than the Schwarzschild radius, then nothing can stop you from falling in and hitting that singularity. You cannot then leave again. You can't go past the event horizon and then return. Basically, the reason is just that the curvature is so strong that it's impossible to overcome it. So let's say that you had a flashlight or a laser pointer, and you turn on the laser pointer near that black hole. Then because the space is curved, that light beam is going to curve around, right? If you have the laser pointer really close to the black hole, you can actually set it up so that the light beam would go around all the way in a circle. It would be so curved that it would come back on itself. This is just a light beam. This is, you know, something we would imagine would go straight, but because the space is so curved, it curves around on itself and comes back. Now, if you had that same laser beam inside the black hole's event horizon, then that light can only go into the center. It cannot ever leave. It can't get farther away from the center of the black hole. Even if you had the laser beam pointed directly away from the singularity, it would go straight into it. So once you're past the event horizon, light cannot escape the black hole. So you might imagine, you know, because light can't come out of the black hole, you might imagine that these things would be dark and invisible and we would never see them, right? Because the light is not coming out. Once light goes toward the black hole, it all falls in. Nothing else can come out of black holes. Things fall into black holes. How would you ever see that they're out there? How would you ever know? Well, it turns out we actually see black holes all the time. Black holes are some of the brightest objects in the universe. The reason for that is because things are falling into them. So this is a plot of a sort of map of X-ray sources in this sort of plane of the galaxy, and all of these little dots in this map are black holes. What we're seeing when we see these sources is actually something more like this. This is just a diagram. This is not an image, an actual astrophysical image. This is just an artist's impression, a drawing. But what's happening here is there's a massive star and a black hole, and they're in orbit around each other. And as the star is orbiting, some of the material from that star gets torn off of the star and circles around the black hole and forms this disk. It's called an accretion disk. And that disk lights up very bright because the material is crashing into itself and heating up. It's kind of like if you have a whirlpool of water and the material in the whirlpool is crashing against the other material. And so you see this sort of frothing as the material is falling in. Even if you weren't able to see the water itself, you would see the crashing of the whirlpool. And it's the similar thing with disks around black holes, accretion disks. The material is coming in, and because the gravity of the black hole is so strong, the material is moving so fast that it heats up with friction, and it collides, and it makes this very, very bright source of light. And we see these things as X-ray sources because the material gets so hot that it glows with X-rays. And so when we see those little dots on that map, those are places where you know, the material from stars is falling into black holes in these accretion disks. So the basic structure is that you have a black hole sort of in the center of this region, and that black hole is pulling all this material in. That makes that accretion disk. And then sometimes in the accretion disk, there are these magnetic fields in that is able to accelerate a jet of material coming out of the poles. So nothing's actually leaving the black hole, but the region around the black hole is getting so heated up and so tangled up, and the magnetic fields are interacting with each other there, and it creates this just jet of radiation that shoots out of the black hole. And we see this in small black holes, in these you know, sort of stellar mass black holes where they're pulling in the material of a star that's orbiting them. But we also see them in black holes in the centers of galaxies. So in some galaxies, in the center of the galaxy, there's a supermassive black hole, which can be millions or billions of times as massive as the sun, and that will have an accretion disk and magnetic fields. And in those cases, the jet coming out of these black holes in the centers of galaxies can be thousands of light years long. So this is a galaxy in which there's a black hole at the center, and you can just kind of see the galaxy as the sort of fuzzy sort of light region there, and there's the center of the galaxy, and then there's a black hole that you can't see in the center here of the galaxy, and it's throwing this jet of radiation across the universe 5,000 light years long. This is a galaxy called M87. And if we zoom in on that region where the galaxy, where the center of the galaxy is, if we were able to zoom in very, very closely, we would see this. So this is the Event Horizon Telescope image of the black hole in M87. This is a black hole that is 6.5 billion times as massive as the sun. It's 55 million light years away. And this image is really showing us something amazing. So this is not just, you know, the usual way we see black holes. This is not just, you know, that we see a point of light because we see material swirling around. This is showing us really the event horizon of black hole. This is showing us the way that the black hole is pulling light out of the universe and into the black hole. So I'll explain sort of the geometry here, what's happening here. Basically, so these are sort of two images, two perspectives on a black hole. So you have, if you have a black hole and you're looking at it from this direction, from over here, right? So this line where it says photographic plate, imagine that's like the telescope that you're looking at the black hole with. As you're looking at the black hole, there's this disk of material that's orbiting the black hole, the accretion disk. Okay, so we're looking at the accretion disk edge on. And the back of the accretion disk, that light should just be flowing out in every direction. But because of the bending of space, the light is bent and curved around the black hole. So we see the accretion disk both above and below the black hole because the light is being bent around the black hole. And then for the accretion disk in the front, that light is able to travel straight to us. So we can see directly the accretion disk in the front of the black hole, but then the place where the black hole is exactly, when we're looking down at the black hole, the light that should be, you know, going in every direction around the black hole, that should be sort of passing near the black hole just gets pulled in. And so there's a region where the black hole is kind of swallowing up all the light, and there's a region where it's dark, where it's just the light is being pulled into the black hole, and we don't see anything. So everything that would have been shining sort of around or behind or in front of the black hole, that light is being pulled in. I'm going to show another visualization of this that may or may not make it a little clearer. So this is a visualization where the accretion disk is blue and white, and this sort of red and black region is representing the black hole itself. And this is just rotating around. So you can see when it's kind of edge on or face on like that, we're just looking down at the accretion disk. There's the black hole in the middle, so you just see the disk as it is. But then as the black hole as the whole system is rotated, you start to see that you can still see the front of the disk, but you can also see the back of the disk behind because the light is being bent around. And as you rotate it even more, you can see that you start to see the back of the accretion disk bent all the way around the black hole, showing up at the top there and showing up at the bottom here. And then when you're looking at it totally edge on, instead of just seeing a line and nothing, you see the disk on the top and the bottom. There are several ways to visualize this. I'm showing a few just to try and give you an idea of what you're really seeing. Here's another a sort of more realistic image of what the black hole would look like from different angles. So here's, if you're looking at it from with the disk totally edge on, here's where you're looking directly down on the black hole. And then these are different angles where you'd see the disk being tilted in various ways, and you can still see it above and below the black hole. Now, one of the important things about these visualizations is you can see that it's a little bit brighter on one side than the other. And that's because the material in the disk is rotating around. It's rotating around the black hole. And so in one part of the disk, the material is moving toward you, and in another part, it's moving away from you. And the part of the disk where the material is moving toward you is brighter because basically the light is being boosted by the motion of that of the material, and it's being brightened it's called blue shifted, but it's being brightened as it's moving toward you, and then the part that's moving away from you is being dimmed as it's moving away from you. And the speed is so high in these disks that can be a really noticeable effect. So, you know, if you look at, for example, this particular example here, you can see that this little sort of line here, this is where you'd expect the event horizon itself to be, and then this is the light from the disk being bent around, and this is basically what we're seeing in the Event Horizon Telescope image. So this again is the real image from the Event Horizon Telescope, where what we see is that this part of the disk is moving toward us, so it's a little bit brighter. This part is moving away from us. We're seeing that boosted light from the black hole. And in here is where we're seeing the effect of the event horizon, the fact that there's part of this light that's just going into the black hole and not coming out again. And the fact that you see that kind of hole in the middle of this image is really telling you that it is a black hole, that it is sort of eating up some of that light, and the rest of the light is able to bend around the object. I just want to say briefly how impressive this image is. When simulations were first done of what this telescope would see, they did these simulations to show how you would see the material moving around. They took a kind of blurry picture of that simulation, and if you compare it to what they actually saw with the telescope, it's an almost perfect match. It's a really incredible achievement that they've been able to do that. And so if you look again at this image, this dotted line, that's about where we expect the event horizon of this black hole to be. And then the disk itself extends, the sort of lit part of the disk is around here. And I just want to give you an impression of how difficult this measurement was to do, how difficult an observation this was to do. So this distance, this sort of size, this is an angular size on the sky. So when I mean angular size, I mean the angle that's made by that object, on the sky. So this is 42 micro arc seconds. So 1 degree is 60 arc minutes, 1 arc minute is 60 arc seconds. 1 million micro arc seconds is 1 arc second. So we're talking about a tiny angle on the sky. For comparison, the moon is about ½ a degree on the sky. So if you look at the moon, you're seeing an angle of about ½ a degree. That the human eye limit is about 0.02 degrees. So you can see some features on the moon just with your eyes. So obviously, if we're trying to look at something that's 100 millionth of a degree, we're not going to be able to see it just with our eyes, right? We need something bigger to see something that small. So you might think, okay, how about we get this giant radio telescope? This is just to give you a perspective on how big that is. This is me here circled in yellow. This is a really large radio telescope. This is a place called the Very Large Array in New Mexico. The limit for this telescope is about 13 arc seconds, or 0.0036 degrees. So still nowhere near that micro arc second resolution that you need. So let's say you take a whole bunch of those telescopes together. So this is also me at the radio telescopes. This is many of them. They use them together as in an array, And then when they put them together in an array like that, it's as though they have a much bigger telescope. It's as though they have a telescope as large as the separation between those dishes. So when they have them all close together like that, they can see about 0.31 arc seconds. When they spread them out, because these telescopes are on tracks, and they can spread them out to be much farther apart, then they make a sort of much bigger telescope. Then they can get to 9,000 micro arc seconds. So we're getting closer. We need to get to about 42 arc seconds, right? So even with this giant array spread out as far as it goes, we're still not getting the right resolution to see that black hole. I mean, the issue is that the black hole is a large black hole, but it's so far away that it makes a tiny angle on the sky, and we just need to be able to resolve that. So what the Event Horizon Telescope did was that they took a bunch of telescopes all over the world and used them together to make one big telescope by combining the data from all these different telescopes. And so if you take the full set of telescopes, then you get a limit of 20 microarc seconds, and that's enough to be able to resolve this image. So what they do is they take all these telescopes all around the world, and then when the light comes through and hits these different telescopes, they combine the information from all the different telescopes and use that to make the telescopes work together as one big telescope. And each one of these telescopes is taking a huge amount of data. It's analyzing all that data. It's putting a huge amount of data together. And so in order to actually combine that data to make an image, you need to take all the hard drives from all of these different telescopes and actually put them into one room and combine that data. So this is an image of one of the scientists working on the Event Horizon Telescope with all of these hard drives from the data from all these different telescopes. And there was so much data, it was 5 petabytes of data, which is just a huge amount. They had to actually take the hard drives and put them on airplanes to move the data. They couldn't send it over the internet. And so what they did, when they took all this data and put it together, you know, you can take the full array data and you get the image we saw. If you remove specific telescopes, you get different pieces of the data, different pieces of that image. So you have to take all that data together, combine it, and then you get this full amazing picture of that object. And this is the first time we've been able to see something so small, so far away, and really put together that picture so that we could actually see the effect of the event horizon and see the light falling into the black hole. So what's next for the Event Horizon Telescope? Well, there's another supermassive black hole that we would really like to look at. This is a drawing, an artist depiction of our galaxy. If we were able to move outside the galaxy and look down on it, we're somewhere around there, and there's a supermassive black hole right in the center there. We call that supermassive black hole Sagittarius A star. We write that as Sagittarius A and then a little asterisk. It's a sort of, it's just a sort of convention, but there's a supermassive black hole there. That supermassive black hole is about 4 million times as massive as the sun. And the event horizon radius of that supermassive black hole is about 10 microarc seconds. So it's you know, it's right around, it's similar to the size of the event horizon of M87's black hole. So M87's black hole event horizon was about 7 microarc seconds. This one's about 10. You know, that whole image was a little bit larger than that. It was about 42. Anyway, so it's a similar size in terms of the size on the sky. Because the black hole is much less massive than the other one, but also closer, the event horizon is a similar size. But it's difficult to see that black hole because we have to look through all of the stuff in the galaxy between here and there. It was very difficult to even see that black hole existed in the first place, which is why just a few days ago, 2 scientists got the Nobel Prize for discovering the supermassive black hole in the center of our galaxy. The Nobel Prize in Physics went to 3 people: Roger Penrose, who is a theoretical physicist, mathematician based at Oxford, who did a lot of the important early work on just proving that black holes should exist, that Einstein's general relativity says that black holes should exist in the universe. And then he's done a huge amount of work on sort of understanding the geometry of the black hole, of black holes and space-time in general. And then Reinhard Genzel and Andrea Ghez are the ones who showed us that there is a black hole in the center of our galaxy, and measured the mass of the black hole and showed us that there was something there. So to give you an idea of what they were actually doing, so this is a picture of the center of our galaxy. There are a lot of stars. There's a cluster of stars in the center of the galaxy, and there's just a lot going on. There's a lot of stars, there's a lot of gas and dust. It's a complicated place, and for a while it's been known that there's a radio source in the center of the galaxy that kind of flickers sometimes. So this is actually an infrared image animation of this source that's kind of flickering there. This source is called Sagittarius A star. As I said, we write it as SGR A asterisk sometimes. And so that we knew that there was something going on right at the center of the galaxy. But for a long time, it wasn't clear exactly what that was. And what Andrea Ghez and Reinhard Genzel did was they were able to observe the stars orbiting around the very center of the galaxy to show that they were orbiting around something very, very massive and very, very small. So this is an animation of the stars in that central cluster going around something in the center of the galaxy. And in this animation, that something is marked with a little hollow star, but really it's whatever it is, you can't see it with telescopes, with optical telescopes. So when you process the images from optical telescopes, you see these little points of light, these stars that are moving around, but you don't see whatever it is that they're orbiting. But if you follow their orbits very carefully and watch how they whip around this central object, you can see some of them move just really fast as they pass around that central object. You can figure out how massive that object is, and you can see that it has to be really, really small because of how close those things get to whatever it is they're orbiting. And that's how we found out that there was a supermassive black hole in the center of our galaxy. Now, as I said, the size, in terms of the visual size, the angular size of that black hole is similar to that of the M87 black hole, the one that the Event Horizon Telescope looked at. The reason it's harder to see our black hole with something like the Event Horizon Telescope is that, first of all, you have to look through all of this gas and dust in the middle, between us and the center of the galaxy. So it's very hard to peer through all that stuff. But also, because our black hole is less massive, it's 4 million times as massive as the sun and not billions of times as massive as the sun. It's sort of the disk of material is moving around it, sort of it's closer in, it's moving around faster, changing sort of more quickly. It's just a sort of more active region. So there's stuff moving around it and orbiting very quickly. And so the brightness changes are faster, and it's harder to see what's going on because everything's moving very quickly. And in order to take those images, you need to watch that. You need to be able to combine the data over several hours. And this black hole at the center of the galaxy is so small that the things around it change over the course of several hours. And so it's just a harder observation to do. But hopefully soon we will have an image of the black hole at the center of our galaxy that's similar to the one that we have for the M87 black hole. So that's going to be exciting. There's one other way I want to talk about how we see black holes. And this is from a totally new way of seeing the universe. So one thing that black holes do is sometimes they collide with each other. So this is an animation of two black holes. It's a simulation of two black holes that are orbiting around each other. And you can see in this simulation the distortion of the light behind them. This simulation doesn't include accretion disks. So all that these black holes are doing is distorting the light that's behind them. And you can see that as they come together, the space is being kind of bent around and moved around. And so you can see the kind of wobbliness of the space around them as they're moving. And what's happening is they're creating waves in space as they're orbiting around. They're sort of wobbling the space around them. They're creating what's called gravitational waves by disturbing the space around them as they're coming together. And that disturbance kind of stretches and squeezes the space around the black holes. And we have now some instruments, some experiments that can detect the stretching and squeezing of space as massive objects move through the universe. So this is called the LIGO instrument, the Laser Interferometry Gravitational Wave Observatory. There are two LIGO instruments in the US, and they are each these 4 kilometer long sort of tubes of like vacuum tubes with laser beams traveling down them. What they're doing is they're detecting the stretching and squeezing of space as black holes collide in other galaxies, rippling the space-time, and those ripples of space-time pass through the Earth and stretch and squeeze those laser arms. So these arms are about 4 kilometers long. And when a gravitational wave comes through and stretches and squeezes the space this thing is sitting in, it stretches it by 1 part in 10 to the 21. So the change in length of this arm as a gravitational wave comes through is about 4 billionths of a nanometer. It's just an incredibly tiny size. It's less than 1,000th the size of a proton. Just a tiny, tiny change in the length, but this instrument is able to detect the changes in the length of these laser arms by that much. And so when black holes collide in another galaxy, causing ripples in space-time, those ripples come through, affect this instrument, and then we're able to see how these arms sort of responded to that. And what happens is, as the gravitational wave is coming through, it gets stronger and stronger as the black holes are really sort of about to merge. And then there's a sort of peak as the merge is occurring, and then the waves sort of settle down again. So what's happening is these laser arms are getting stretched and squeezed and stretched and squeezed, and the stretching and squeezing speeds up and it gets stronger. And then the merger happens and it calms down again. And so that pattern of the stretching and squeezing of space is what we expected to see when these calculations were done. And these calculations were done sort of in 2005. And then when the first black holes, the first time the LIGO instrument was turned on and was able to do a detection, it saw exactly the same pattern in the changing of the length of these arms. So this pattern of the stretching and squeezing and then the collision of the black holes was exactly what was predicted years before the machine really turned on. So it's an incredible thing that this machine is able to detect the stretching and squeezing of space from black holes colliding in another galaxy. I just still find that kind of amazing. And as this thing has been operating for several years, it's found the mergers of many different kinds of black holes. So all the blue sort of circles here are black holes of different masses that the two black holes came together and created a new black hole of of a combined mass. So each of these is, there's a, one black hole meets another black hole, and they make a larger one. And in that collision, in some cases you can have, I think, so the first one that was seen, you had two black holes that were each about 30 times as massive as the sun, and they collided with each other, and then they emitted gravitational radiation, and the amount of gravitational waves, the amount of energy in that stretching and squeezing of space-time was as much energy as if you took three suns and just converted them completely into gravitational waves. So it was just a huge amount of energy that was spread across the universe as those black holes combined. And this one that's highlighted here is the most recent collision of black holes, where really very massive black holes were colliding together to make something extremely massive at the end. And we're still sort of trying to understand how black holes get that massive. So I've talked here about two different kinds of black holes. I've talked about stellar mass black holes, so the black holes that come out of just the collapse of a star. And those usually tend to be born around 5 to 10, maybe 20, 15 times as massive as the sun. And then there's supermassive black holes that are formed through different processes, and those can be millions and billions of times as massive as the sun. And the black holes that LIGO has been detecting are kind of more in the tens of solar masses range, and we think that those can be formed by the collapse of massive stars. But when they get to be these higher massive ones, we don't know exactly how those form. There might be other processes where a star collapses and then more stars get eaten up by that black hole, or it pulls in a whole lot of gas. We're still trying to understand exactly how black holes form and grow. And one of the tools that we're going to be able to use in the near future is pulsars. So I mentioned pulsars toward the beginning. These neutron star things that shoot out these jets of radiation I showed in the Crab Nebula. This pulsar that was living there, it's a remnant of a massive star. If we look at pulsars around us in the cosmos, we can see that there are lots of pulsars, and they have this very regular rotation, this very regular sort of pulsing of radio waves. And so we can use these pulsars as sort of signposts to see how the space in between us is being distorted by the presence of gravitational waves from distant black hole collisions. So we're starting to be able to use the timing of pulsars in something called a pulsar timing array to hopefully detect black holes and gravitational waves in the future. And the kinds of black holes that these things will be looking for is supermassive black hole collisions. So the black holes at the centers of galaxies, if two galaxies collide, then those the black holes at the centers of the galaxies can collide too. So, they'd be black holes as big as the ones that the Event Horizon Telescope saw, but those colliding with each other. And this is an image of what we think is two supermassive black holes in the center of a galaxy where a collision of galaxies has occurred. So I think I'm more or less out of time now. I'll just say that, black holes are one of the most important mysteries in the universe today. And they're not mysterious because we don't know about them. They're mysterious because they hold within them a lot of uncertainties and questions about how gravity works, how space-time works, how our universe works. And we're starting to be able to really understand them as astrophysical objects. So we're able to see them in our own galaxy. We're able to see supermassive black holes in other galaxies. We're learning about how they merge with each other over time. We're learning about how they grow, how they pull in material. We can watch them light up as they pull material in. We can watch the jets of radiation come out. We can see their evolution over time, and we're starting to learn about how supermassive black holes and galaxies interact with each other and how they grow over time. So we're learning a lot about them as astrophysical objects, and with experiments like the Event Horizon Telescope and LIGO, we're starting to learn more about the strong gravity that they have around them, and how that strong gravity fits into our ideas about physics, gravitational physics, general relativity, and possible new theories about gravity and about how fundamental physics works. But there is still a lot of really big questions about how black holes work in our universe, how what they might tell us about the connections between gravity and quantum mechanics, how they connect to sort of fundamental physics, and how they might change in the future in the universe, and what we can learn from them. So it's a fascinating area of both physics and astronomy, and it's someplace where I think that we're going to just continue to learn amazing new things into the future. So with that, I will end my presentation, and I will take questions. Thank you.
Okay.
Thanks.
Well, thank you very much, Professor Mack. Clearly a ton of ideas and things to stimulate the imagination. We had over 30 questions, which we're not unfortunately going to be able to get to, but I'm gonna I'll choose a few of them which have either been upvoted or I think are of very general interest. So one question that came up a number of times. Apparently, people are big movie watchers. And there were some questions about the film Interstellar. And in Interstellar, the hero of the picture is a black hole, is how the astronauts interact with the black hole. So the question is, how realistic is the black hole in Interstellar?
Right. Well, so the thing that's the most realistic about the black hole in Interstellar is what it looks like. So if you remember in the film Interstellar, the black hole had that shape that I sort of showed, where you have, you can see the disk in front of it, and you can see the disk above and behind it, and it makes this kind of sort of circle with a line through it. And if you watch carefully, the way that the light moves around that black hole, it's a really beautiful simulation, and the way that they did that is basically Kip Thorne, who is the science advisor for the film. He told the movie graphics people what they needed to do. And he and his collaborators put together the equations for what a black hole should look like how the gravity should distort the light, and they gave it to the movie graphics people, who have these amazing image processing engines, and they were able to use the film to do research to actually run their simulations on the Hollywood computers. In order to get the picture right, but also to do new basic simulations of how black holes should appear, and they published some papers based on this, actually, based on the calculations that they did with those Hollywood computers. So that the image of the black hole in that film is really very correct. The only tweak they really did is they made the accretion disk a little bit dim in order to not overwhelm the picture, and they made that brightening of one side not so strong, so that because I guess they thought it looked weird, but otherwise it's an incredible visualization of a black hole. In terms of the science otherwise, one thing that happens in the film is that they go into the black hole. That's not a good idea. You should definitely not do that. you know, you would definitely be killed. You should not try and go into a black hole. They made use of some sort of very, very speculative, questionable ideas about how the space-time and black holes might connect to other regions of space. I wouldn't take too much of that seriously. There are theories that connect with some of those ideas, but most likely if you go into a black hole, you just die. That's kind of where that goes. There is a book that Kip Thorne put together called The Science of Interstellar that discusses all these topics in much more detail and explains the places where he used sort of speculative ideas to justify some of the science fiction plot. So I would definitely recommend looking at that book, The Science of Interstellar, if you want to learn more about what went on there. I also wrote an article a while back for the internet about the, you know, all the things that happened in Interstellar and which ones were backed by science or not. So you can probably find that on Google somewhere. I wrote it for BuzzFeed with another person. So check that out. But yeah, don't go into a black hole. I don't recommend it.
It's great when science and art can join together in a way that
yeah,
you know, adds something to each.
Yeah.
So actually related to your last point, a number of people asked, what is the difference between a black hole and a white hole and a wormhole?
Right. So a white hole is a theoretical object. So a black hole is a region where if you get too close, you can only go into it. You can't go the other direction. A white hole is a theoretical object that would have the opposite property, where if you were close to it, you could only go away from it. So it would be something that only sort of emits rather than pulls in. We don't have any evidence that white holes exist in the universe. So it's not clear how they would be made. But it is possible to write down equations that would describe how they would behave if they did form. As for wormholes are a theoretical possibility where space could be bent such that it bends in, and then instead of going to a singularity, makes kind of a pathway from one part of space to another. So you would connect two regions of space through a kind of tunnel. That's how a wormhole would work. You would enter in one place and exit somewhere else, and so there's no event horizon. But if you could pass through the wormhole to a different region of space, and it would connect different parts of space. In principle, like it is possible to write down equations in general relativity that describe wormholes. And Kip Thorne, in fact, is one of the people who has done that, has put together possible descriptions of wormholes in general relativity. We don't have any evidence that those exist in the universe either. And when theoretical calculations have been done, generally speaking, once you set up the equations for a wormhole, it immediately collapses. It's very hard to keep it open. So you have this kind of path between two regions of space, this kind of tunnel. It's very hard for that tunnel not to just collapse on itself gravitationally. And there have been some studies describing ways that could be held open with some kind of exotic sort of matter energy source that may or may not exist in the universe. But the idea that you could actually travel through a black hole, the idea of a traversable, travel through a wormhole, a traversable wormhole is very hard to set up theoretically. And we don't have any evidence that they exist in the universe, and we don't know how one would be created. So at the moment, wormholes are an interesting theoretical idea, but probably not, you know, a practical or astrophysical object.
Great. Looking a bit to the future, one of the questions is saying, could you make the Event Horizon Telescope array even better? What would you learn from it if you could put a radio telescope in space or on the moon?
Yeah, so there has actually been discussion of doing that. The difficult thing is, I mean, obviously there's the difficulty of putting something out into space or on the moon. Like, just that's just a hard thing to do because you have to launch it and everything. The other thing is that you have to get the timing very correct. You have to know exactly where that instrument is, and you have to get the timing right, so that when the radio wave comes in, the radio wave will come in and it'll hit that telescope and the telescopes on Earth, right? So you'll have two separate things. You'll have the one in space and the one on Earth. And when the radio wave comes in and hits those two instruments, you need to know exactly when it hits and exactly where those instruments are with respect to each other, to a very high degree, in order to be able to combine those images usefully. So you would have to be keeping careful track of where the telescope is, and you'd have to get the timing right. So having it in orbit might be complicated because it'd be sort of moving over the course of your observation, and you don't really want it to do that. Having one on the moon might be better if you, depending on how you do it, but it would be very difficult just logistically to combine the data, and to get the data back, because you'd have a lot of data that you need to bring back. And in this case, excuse me, with the Event Horizon Telescope on Earth, they had to move the data around by putting it on airplanes because there was so much of it. If you have something in space, the data exchange rate is going to be very slow, so it's going to be hard to do that combination. But in principle, yeah, it is something that you could do to get a larger separation. But the other thing to note is that even if you have a large separation, you do lose a little bit by having sort of very little coverage of the region in between. So so there are some trade-offs, but I think it's something that can be done. It's just, practically speaking, it's a little bit hard. And I think right now, mostly what they're trying to do is to just improve the number of telescopes and the size of telescopes on Earth. But I think there is discussion of bringing in a space telescope, and hopefully the logistics are something that can be worked out.
So something for all the students in the audience to work on in their careers.
Yeah.
All right. As I say, there's over 40 questions. I'm just going to ask one final one, looking even further to the future and connecting to your book, The End of Everything. And the question is, are all the stars eventually going to become black holes? Is the entire universe in the future eventually going to collapse into one giant black hole?
Great. Yeah, that's a great question. I actually had some backup slides about the future of the universe, but I didn't quite have time to get into those. So a lot of things will become black holes in the future. So as the stars in our galaxy burn out, most of them will become white dwarfs and then what we call black dwarfs. So they will just be these very compact remnants that will just cool over the course of billions and billions of years. In a lot of cases, they will be orbiting each other, and they will eventually combine. And if they have enough mass, they will become black holes. And a lot of the stars in our galaxy will eventually, their orbits will decay, and they will end up in the supermassive black hole in the center of the galaxy. So if you have enough time, a lot of things within our galaxy will become black holes, or will combine into the black hole in the center of the galaxy. But also eventually, we think probably matter itself will decay. And so there will probably be some black dwarf stars that will just decay away on their own without ever combining with anything else to become black holes. And then the black holes themselves, we think, will evaporate. So if you leave a black hole alone long enough, then it will, through a complicated process with quantum mechanics, will sort of lose mass around the edges. It'll just release a little bit of radiation around the edge of the black hole and start to shrink. And so we think it takes a very long time. So the black holes that we know about in our universe, even the smallest ones, will take something like 10 to the power of 70 years before they will fully evaporate, if you just leave them alone. So it's a very, very, very long time that process takes. But eventually, we expect that those will evaporate. The reason that, what you won't get is you won't get everything collapsing into a single black hole. Even if our own galaxy, if most of the things in our own galaxy end up in the central black hole, other galaxies will be so far away and will be carried away from us so far away so quickly by the expansion of the universe that they will never interact with us again. So in our little region of space, there will be some black holes and those will evaporate, but we won't combine with other black holes in other regions of space. For the most part, the future evolution of the universe will be toward a very, very empty space. And even, as the black holes evaporate, as the matter decays, things will just get emptier and colder and darker and more spread out. And there are a few other possibilities for what that evolution looks like into the future. And in my book, which I'll just show you because I have it right here. This is my book. In this book, I go through kind of 5 different possibilities for the end of the universe. And there are some different possibilities for, it is possible that something could change where the universe could collapse on itself. There's also a possibility where the universe could undergo a transition that creates a bubble of a different kind of space. And that could destroy the universe. And in that scenario, that could in principle be triggered by the evaporation of a black hole. So that's another way that comes into the picture. So there are a few different things that I didn't really have time to get into there, but you can check out the book if you're interested in the details of that.
All right, wonderful. Well, thank you very much for giving us so much to think about today.
Thank you.
If people still have further questions, on the poster, on the email that was sent out is Professor Mack's Twitter address, so you can ask her there. Mm-hmm. And I also want to point out that right here at Nazarbayev University, the Department of Physics, a number of the professors do research on black holes, on radiation from black holes. Some people were asking about Hawking radiation. So black holes have a number of fascinating things, and you can talk to the physics department people as well as to Dr. Mack on Twitter or on the web. So thank you all for joining us today. And next week, we have another Autumn Colloquium on the search for alien life and how to use radio telescopes to do this. So please join us next week. The announcement will be sent out shortly. Thank you.
Thanks, everyone.